All right, covered in Appendix F are some known sums and their proofs. All right, there are 5 known sums that you want to memorize. Okay, and so I'm just going to give them to you so you have them nice and handy and together. But I am also going to show you the proofs, the proof of each one here. All right, so first, known sum. If we add up all the numbers from 1 to n of 1, right? If we add up 1 n times, we will get n. Okay, first one. The second one, if we add up a bunch of constants, right? If we add a constant n times, we're going to get the constant times n, right? We're going to get the constant plus constant plus constant plus constant n times, right? The next one is the summation from I equals 1 to n of just I, right? So if we add up 1 plus 2 plus 3 plus 4 plus 5, right, and we keep going and we stop at n, we're always going to get n times n plus 1 divided by 2, right? A very famous mathematician solved this when he was in grade school, right? His teacher was getting annoyed with him. He always knew the answer to everything, and so the teacher said, "Boy, just go up, add up all the numbers from 1 to 100. And the class gasped, and he came back in about 5 to 8 minutes with the correct answer, and it didn't matter how many numbers she told him to add up. He could just use his formula and get the answer rather quickly. So this, we will kind of use his strategy here in order to prove this. It is really very interesting. All right. So then the next sum is, what is the sum of I squared? Right. So the sum of I squared is n times n plus 1 times 2n plus 1 divided by 6. All right, we will prove this one. Okay, the proof is by induction, and you have not seen a proof by induction, but there's no time like the present. All right, we might as well kind of let you see one. So then the third one, maybe I shouldn't put it next to the border there. The last one, okay, the final one here, the fifth one. I know I said third. I was thinking I squared and I cubed. But I equals 1 to n of I cubed. Okay, we're always going to get n times n plus 1 divided by 2 quantity squared, right? So it is kind of interesting that it's just the I summation squared, but we're going to prove this one by induction as well. So these two are fairly straightforward. This one we're going to prove just normal methods, and then these two need to be proved by induction. All right. So first, the proofs. All right, proof of A. So the summation from 1 to n of 1, right? We know the answer should be n. So what's going to happen here? The first term is going to be 1. The second term is going to be 1. The third term is going to be 1. All the terms in between are going to be 1. And how many times are we going to do that? Okay, we're going to do that n times. So 1 plus 1 plus 1 n times is n, right? And that's just how the proof goes. All right, B, the proof of B, proof of B is the summation of a constant, and it looks just like the first one. We could just do C plus C plus C plus C n times, Or, because it's a constant, we could factor the constant out in front. So this is just going to be a constant. And if I take the constant out in front, what's left here? Okay, if I take a c out of c, I'm just left with 1. Well, this we just proved, right? The summation from I equals 1 to n is just n. So we're going to get c times n, all right, if we kind of rely on what we just proved. All right. So then the proof of C and C says we have the summation from I equals 1 to n of I. Okay. And we should get n times n plus 1 divided by 2. All right. So what I'm going to start off with is doing the sum from 1 to n of I. Okay, so this is 1 plus 2 plus 3, okay, plus n at the final. And I'm going to call this sum S. All right. So what I'm going to do is I'm going to add S with S, but I'm going to add it very carefully. All right. So the first time I'm going to add S, I'm going to write it in an increasing manner. So 1 plus 2 plus 3 plus, right, and then we're going to get to n here. All right. Now I want to add S to itself, but instead of doing 1 plus 2 plus 3 plus, I'm going to go backwards. All right, so the last number is n. The next to the last number is n minus 1. The next to the last number is n minus 2, right? And we're going to keep subtracting 1 until we finally get to 1, right? So here's increasing summation, and here's the decreasing summation, but they both equal S, right? So what I'm going to do here is I'm going to add these summations to each other, right? So S plus S is simply 2S, right? Now if I add each column here, 1 plus n is n plus 1, right? 2 plus n minus 1 is what? Another n plus 1. And then if I add the third term, 3 plus n minus 2 is another n plus 1. So you can kind of imagine we're going to get a whole bunch of n plus 1s. And even the last term, when I add them together, I have n plus 1, right? Now, how many, right? How many n plus 1 do I have? Well, this sum had n terms. This sum had n terms. So this sum has to have n terms, right? So there's n of these. We're going to add n plus 1 n times. So now I have 2 times the summation is n times n plus 1, right? Because there's n of these n plus 1 sums. And so now you can see it, right? You divide by 2, and you get the sum is n times n plus 1 divided by 2. Now, that's pretty interesting, right? So when, I think it was Gauss, okay? So when little Gauss was adding up all the numbers from 1 to 100, right? He kind of started by noticing that 1 plus 100 is 101. 2 plus 99 is 101, right? 3 plus 98 is 101. And how many 101s did he get? He got half of 100, right? So let me go ahead and do this. So this plus this is 101, right? This plus this is 101. Okay, 3 plus 98, another 101. How many times could he do that? Well, only half the number, right? So he got 101 times basically 50, right? So this is our n plus 1. 101 is our n plus 1, and 50 is our 100 divided by 2. Right? So that's how he kind of added them up so quickly, which is really interesting. Oops, I don't know why I'm crossing that off. All right, so it's n times n plus 1 divided by 2. All right, it's a cool little proof. All right, so now let's do the proof of D, all right, which is a proof by induction. I have to warn you, I'm not looking at any notes when I do this. I have the proof by induction for E, but not D. Oops, proof of D. All right, so D says we want the summation from I equals 1 to n of I squared to be n times n plus 1 times 2n plus 1, all divided by 6. All right, so in a proof by induction, we have to do 3 things. The first thing we have to do is we have to show that the case where n equals 1 is true. Right? Case where n equals 1 is true. Show that the first case works. Right? And then the second thing we have to do is we're going to assume the n equals k case is true. And we're going to use that n equals k case to prove the k plus 1 case is true. All right, we're going to do those 2 things. All right, so the proof here, the first thing we're going to do is we're going to show that the case for n equals 1 is true. So if I were to plug 1 in for n, I'm looking at the sum from 1 to 1 of I squared. Right? So the sum from 1 to 1 of I squared is just 1 squared, which is 1. Okay? So we know what the sum is. Now, does the formula work? If I plug 1 into the formula, will I get 1? So we're going to get 1 times 1 plus 1 is 2, times 2 plus 1 is 3, and then divide that by 6. All right, so the formula works for the case equals n equals 1. All right, so the next thing we're going to do is we're going to assume the n equals k case is true. All right. All right, so what that means is that the sum from I equals 1 to k of I squared equals k times k plus 1 times 2k plus 1 divided by 6. All right, we're going to assume this is true. And what we want to do is we're going to use this in our proof of the k plus 1. Right? So prove that this sum, I equals 1, I shouldn't have wrote that so big, to k plus 1 of I squared equals, all right, I want to go ahead and figure out what the k plus 1 case is, right? So if I were to plug k plus 1 into this formula, okay, I'm going to get k plus 1 for the first factor. If I plug k plus 1 in for k, I get k plus 1, which is k plus 2. And then if I plug k plus 1 in here, 2 times k plus 1 is 2k plus 2 plus 1 is 2k plus 3. All right. So in the end, I'm going to look for this summation to prove the next one. All right. So I'm looking for k times k plus 1 times k plus 2 times 2k plus 3 over 6. Right? So what is the sum of I equals 1 to k plus 1 of I squared? Right? Well, I can break this up to the sum from I equals 1 to k of I squared. Actually, you know what? Gosh, I told you I'm not looking at anything. Let's go ahead and enumerate this, right? So we're going to get 1 squared plus 2 squared plus 3 squared, and we're going to go all the way. Let's go ahead and do k squared, and then we're going to get our last term, k plus 1 squared, right? Everybody agree? So if I were to enumerate what the summation says, right? 1 squared, 2 squared, 3 squared. Now, I know what all but the last term equal. If I sum from 1 to k, I am going to get this, right? So what I'm going to do is I'm going to substitute all of this with k times k plus 1 times 2k plus 1 divided by 6, right? And then I just need to add to that k plus 1 squared, right? So how do we do that? Okay, how do I add this and this? Now it's just algebra, all right? So let's go ahead and get a common denominator, all right? So I'm going to multiply this by 6. So now I have k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared all over 6, right? So here what I can do is I can factor out a k plus 1 out of both terms. So if I factor out a k plus 1, I'm going to be left with, in the first term, k times 2k plus 1. And then in the second term, I'm going to be left with 6 and a k plus 1. All right. So then I'm just going to simplify what's here in the bracket. So here's my k plus 1 that I factored out. Inside here, if I distribute the k, I get 2k squared plus k plus 6k plus 6. So I have k plus 1. Inside the bracket, what do we got? 2k squared plus 7k plus 6. Sorry for writing really small here. All right. Now, 2k squared plus 7k plus 6. Let me go up here. This factors, right, to k and 2k. I need a sum of 12. I'm sorry, a product of 12 and a sum of 7. So I'm looking at 3 and 4. All right, so it factors to k plus 2 times 2k plus 3, right? Because I'm going to get 2k squared, 3k and 4k is 7k plus 6. Right, so now I get k plus 1, and then I'm going to factor this, sorry, I'm going to factor this binomial here to k plus 2 times 2k plus 3, and that's still all over 6. And look, that's exactly what we should have got, right? By just plugging k plus 1 in the formula, we were able to prove it. All right, so there's your first proof by induction. Fun, right? All right, we got one more. Okay, one more proof, and that'll end this video here. So let's do the proof by induction of I cubed. All right, so E states that the sum from I equals 1 to n of I cubed is n times n plus 1 over 2 squared. Right? So again, the proof by induction, we're going to show that the n equals 1 case is true, and then we're going to assume n equals k is true, and we'll prove the k plus 1 case. All right, so proof by induction. The case n equals 1. Right? So the case n equals 1. So if we do the summation from 1 to 1 of I cubed, we should just get 1. Right? So we want to verify that the formula also gives us 1. So if we plugged 1 in for n, right, we're going to get 1 times 2, which is 2, right? 1 times 2 divided by 2, the 2's are going to cancel, and we're still squaring 1, all right? So the formula works for 1, all right? So then we want to assume that n equals k is true. So we're looking at the summation from I equals 1 to k now. And so the k case, if we assume the formula works, is going to be k times k plus 1 divided by 2. Right? So if we assume this is true, then we want to prove the k plus 1 case. Right? So the k plus 1 case, if I just replace the k's with k plus 1, we're getting k plus 1 times k plus 2 over 2 quantity squared. Right? This is what we're looking for. All right? So let's start off with just a simple summation of the summation from 1 to k plus 1 of I cubed. So if I were to enumerate all of these terms, we'd get 1 cubed plus 2 cubed plus 3 cubed, and we would keep going, right? And we would get k cubed, and then finally we would get k plus 1 cubed. And so just like last time, we already know what the sum of the first k terms are, right? We can assume that the formula works for the first k terms. So all of this right here, the first k terms, is equal to k times k plus 1 divided by 2 quantity squared. Right? So what I want to do is I want to add k plus 1 cubed to that. And if I get a common denominator, I should be able to simplify it to what it equals. All right, so let's go ahead and do that. What is this thing squared? We're going to get k squared times k plus 1 squared over 4. Agree? So then we want to add to that k plus 1 cubed. So if I wanted to get a common denominator, I'm just going to multiply this by 4 over 4. And so I'll get k squared times k plus 1 squared plus 4 k plus 1 cubed all over 4. All right? So just like last time, we have two terms, and it looks like I could factor out a k plus 1 squared. So if I factor out k plus 1 squared out of the numerator, then in the first term I'm just left with k squared. And in the second term, I'm left with 4 times k plus 1. And this is all over 4, right? Oops, okay. So then what I got, if I were to multiply this out, I have k plus 1 squared times k squared plus 4k plus 4 over 4. Well, k squared plus 4k plus 4 factors, right? So multiply to 2, multiply to 4, add to 4 is k plus 2 and k plus 2, right? This is just k plus 2 times k plus 2. So we have k plus 1 squared, and then inside the brackets we have k plus 2 squared, and on the bottom we have 4. So guess what we can do? We can just rewrite this as k plus 1 times k plus 2 over 2, and then square the whole thing, right? And there we have proven what the k plus 1 case should be like. All right, so I hope you've enjoyed these proof by inductions. I sure enjoyed showing them to you. All right, take care, guys.